we presented the work we are doing on in situ upgrading, trying to use nanoparticles as catalysts and create the conditions in the reservoir to produce upgrading and extract an oil that can be directly pipelinable with a minimum upgrading at the zone of the northern Alberta, capable of entering a refinery directly from there. That work continues. Last year we also explained that the advantage of the method we use is we prepare microemulsions, nanoemulsions, or conventional emulsions with very short lifetime. So we decompose the particles very quickly or produce the active phases very quickly. Every drop in that emulsion or microemulsion contains all the ingredients to make selective the process of fabrication, manufacturing the active phase of catalyst that we want. And today I'm going to just present one application that we consider is pretty much ready for scale up and demonstration. We are working this with a couple of companies, unfortunately outside the oil sands sector. We're working in Colombia with an oil company, and in Germany with also another oil company to try to apply the technology to our best. The company then that we formed for as a spin-off of our activities is has been interacting in three ways with with the wide sector of industrial application of nanocatalysts. We are trying to do technology transfer basically on the in situ upgrading area. We are also working on consulting contracts to see the viability of applying nanocatalytic technologies in some cases, and in particular we have these two joint contracts to support the R&D development that I'm going to be talking about. The way we operate very quickly is we establish E/C research contracts in which we perform experimental projects to demonstrate the inventions that we have. That experimental project generates data that the industrial partner would analyze, and eventually if he considers we can progress, then we can do all the engineering process schemes and steps needed for eventual application of the technology. And for that is that Texera solution was created. Okay, what is it the technology we are concretely talking about in this case now is a surface technology, but it departs from the conventional upgrading in the sense that it doesn't use thermal reactions, so it doesn't generate coke. Also, it doesn't use hydrogen, it uses steam and dissociates in the reactor the steam to produce the hydrogen needed for upgrading. The oxygen from water would go and form CO2. The extent of the cracking that happens because of the presence of dissociated water would produce CO and CO2, which is very minor compared to the hydrogen production, conventional production, which produce large amounts proportionally of CO2. The fact that we generate hydrogen in the place makes much more effective the use of hydrogen being generated. So the aim of this technology is to apply it in remote areas, field production facilities, and the aim is obviously to produce transportable quality. We cannot hydrogenate directly aromatic rings with hydrogen coming from water. Thermodynamics says that is not possible, but we can crack and saturate with hydrogen coming from water, and that is primary cracking, which is enough to produce a significant reduction in viscosity of the oil, as you will see. Our catalyst is originally in the range of 30 to 50 nanometers, and here is the particle size analysis after reaction. This catalyst can be submitted to a recycle in the reactor, and this is what we call the equilibrium catalyst after several passes through the reaction zone to produce upgrade. So we are talking about a particle that centers after equilibrium in the range of 70 to 80 nanometers range, and starts in the range of 30 to 40 nanometers when it is entered into the reaction conditions. Okay, the options of this catalytic upgrading technology. We talk about, and this is the initiative we're carrying out right now with the Colombian oil company. It's feedstock crude oils in the range of 10 to 13 API. They are mobile in the reservoir. They cannot be transported conventionally in pipelines, so they need diluents because the country is not as vastly developed probably as we may have here. Then they don't have facilities to, not even routes to transport significant equipment there. Also, the carrying of diluents makes very expensive the exploitation. On top of that, the availability of diluent is very critical in those zones. But then this oil is not too far from getting to transportability conditions. So probably by upgrading a fraction of it, we can get some advantages. And this is what we have done as research for them, just trying to take the technology adapted to the specific need of this oil. In this particular case, then what we need is just to perform an atmospheric distillation or a topping and vacuum distillation, and just with one single reactor without touching the vacuum residue, so without unstabilizing, without producing any coke, we can just use part of the vacuum residue as fuel for the needs of the upgrader. And the catalytic reaction with steam takes care of the vacuum gas oil fraction, which is then transformed into much lighter products. The catalyst is recovered, and that solid can be reused in a loop here. So a minimized production of solids in the site is obtained. And we produce a synthetic oil which has not been touched in terms of asphaltenes. There is a total stability of the oil. And however, we get that way a totally transportable crude oil that could be processed in a refinery. The second option is to apply this, and we are handling this with a German company to an oil, for example, in Russia. And the feedstock crude oil in that case is 9 to 10 API, and the goal is again to improve viscosity. And on that configuration, we can also perform just a simple topping and increase the span of hydrocarbons to be steam hydrocracked. Then the catalyst, then the bottom of the barrel is of the column, of the topping column, also a long atmospheric residue, is de-asphalted, and asphalt is used as fuel. The DAO, which is a very long DAO from heavy gas oil, atmospheric gas oil, all the way to vacuum residue type of molecules, but not containing asphaltene, is processed again in the same catalytic steam cracking reactor, and we have a synthetic crude oil. In that case, we don't touch the asphaltenes, and the fraction not used can be remixed and form synthetic crude oil. So the third option is an oil to increase the higher conversion, and then we get a slightly different configuration. And at the end, we can compare all the oils that we may produce using these nanocatalytic technologies. You can see that for a case of 50,000 barrels capacity, we only use a 10% or less fraction of that capacity for energy purposes. The API gravity can be improved to 17 API, 16 API, in the range of 15 and let's say 18 API gravity. But what is notorious is a change of viscosity in the range of 100 at centipoise at 25 degrees C, with a significant reduction in investment of inside battery limit only of in the range of $210 billion for the 50,000 barrels development, with a very low efficiency in terms of OPEX, and with a complexity level more important that is of much lower than what any conventional refinery may afford. So this is a very low footprint of upgrading activities in the field. I'm going to skip all this information just to tell you that The advantages of COD are clear here to conclude. 3 different schemes allowed for processing a wide range of heavy crude oils. COD do not tackle asphaltene for conversion, thus no asphaltene stability issues are produced. Oil corporation business growth by increasing heavy oil production with a minimal use of diluents or no use of diluent at all. There is a low investment implied and with a low complexity factor. There is an original, well-mastered chemistry that supports this development. We've been working on that for a long while, and we can provide technical assistance backed up by a professional team that has a vast experience in heavy oil and comparing technologies of other type with this same type of nanotechnology. Thank you very much.